Okay, now I rolled a ball down 3 ramps. Okay, one ramp had a slope of 1 unit in 60, 1/60th. 1 centimeter divided by 60 centimeters is just 1/60th. There's no unit to this. When you divide the rise of a ramp by the run, you're dividing units of length by units of length. The units of length therefore divide out, leaving you a unitless quantity, which is the slope of the ramp. Okay, and then we had another one whose slope was 2.5 over 60, another whose slope was 5 over 60. So I put those quantities more or less where they ought to be on an axis and labeled that axis ramp slope. Then we calculated accelerations based on some data that I got. Now that's what we want to talk about. We want to talk about how I calculated those accelerations. Now I first did estimates. I counted 1,001, 1,002, 1,003 after releasing a ball from the top of the ramp. And at 3 seconds I came up with actually a pretty good estimate. I thought it was about 54 centimeters down the ramp at that instant. Now this is all subject to my counting, okay? And need to move the camera over a little. Okay, it's subject to my counting, so it's not a particularly accurate result, but I'm pretty good at counting evenly, so I'm expecting I got half decent results here. Okay, I then changed the slope of the ramp and observed that in 2 seconds the thing moved just about the same distance. So I'm going to say it's 54 centimeters. Now actually my estimates would have been different by a couple of centimeters, but I wanted nice numbers that could be divided by like 3 seconds and 2 seconds. So I kind of fudged a little bit, but yeah, that's within about 2 or 3 centimeters where I really think it was. Okay, and then on the steepest of the ramps, it was down past the end of the ramp in 2 seconds. It made it to the halfway point in 1 second, a 60 centimeter ramp. So I'm saying it's at 30 centimeters after 1 second. Okay? So we have this data, and now we want to calculate the accelerations. And of course, we can go to kinematic equations, initial velocity being 0, displacement being 54 centimeters, time being 3 seconds, plug it into a formula, get the result without understanding anything about what that means, what that's telling us, or how that's related to what's actually going on the ramp. But we can get the answer. Okay, and sometimes that's enough, but that's not where we want to be right now. We want to understand it more deeply than that. So we do this by using graphical methods, because this is a good exercise in understanding what graphs are telling you. And from what we saw in class, people really need some work on what graphs are telling you. Okay, the things that you do in calculus can all be, well, in most cases, almost all, be represented graphically and can be interpreted in terms of different situations. But again, that doesn't always get done because you're too busy learning the rules to differentiate and integrate and so forth. So, but you gotta bring that together now. Okay, so what I'm saying is that well, I ask you to do a V versus T graph for each of these situations. Okay, and then I kind of drug the rest of this out of you. Now, the V versus T graph is going to be a straight line. Why? Well, you should know, and you should know why, but nobody really seemed to be able to explain it to me, that the V versus T graph should be a straight line. Okay? Now, you do know that in one significant connection, and it's good that you do know that, because if acceleration is uniform, you've got this function for the position, and the derivative of that function gives you the velocity. This is a quadratic function. You know that the derivative is going to be linear. Okay? Derivative of a quadratic is linear. And you just take the derivative and you see the t squared, when you take the derivative, gives you a t term. The t term gives you a constant term. The constant term goes away. That's a linear function. V of t is a linear function. We could write out what the function is. You know, it's ax times t plus v naught x. That's your v of t function. It's a straight line with a slope equal to the acceleration. And since I had to make the distinction between the acceleration and the a in your quadratic form of the function. I should call that a sub x. Slope is a sub x. And the y-intercept, well, you figure out what the y-intercept is. I just took the derivative. I just said what the function is, so take the derivative, look at it, tell me what the slope is, what the intercept is. You should certainly understand that about the straight line. If you don't, you need to think it through, so you will. Okay. Now, again, velocity versus time graph is a straight line. Okay? Then I asked, what's the first thing you're going to do if you want to make that graph? Well, you take the 54 centimeters into 3 seconds. Everybody divides that. Everybody says, well, that's 18 centimeters per second. Okay, well, very good. My next question, well, what does that represent about the motion? And somebody said, well, that's the motion at the end of the interval. At 3 seconds, that's how fast you're moving. And I said, okay, well, let's kind of test that. And I actually said, well, that's not right, but let's see why it's not right. Okay, and then it took a while. And I asked, okay, well, what quantity here would you label on a graph of v versus t? Some people wanted to label 54 centimeters. Well, you can't label 54 centimeters on this graph, although 54 centimeters is one of the characteristics of this graph. It's not really something you can directly label. And you have to know what it is to label it. So we're going to see what it is, but right now, that's not a v quantity, that's not a t quantity, so it makes no sense to label it in the graph. Of course, you already see the graph being labeled, but we're talking, we started with an unlabeled graph, none of these lines were there. We had to reason out step by step how to label the graph. Okay, the only thing you can directly label immediately is the 3 seconds with any confidence, and 3 seconds is going to go somewhere on the t-axis. It could go anywhere because this graph is initially unlabeled. There's no scale on it. As soon as you label the 3 seconds, now you've got a scale for the t-axis. So we take the unlabeled graph, straight line through the origin. Incidentally, it's through the origin because this thing started from rest, so the velocity was 0 when t was 0. Okay, we label the 3 seconds. Now we have a point on the graph that corresponds to the 3-second time and the final velocity. Okay, now we hadn't labeled any of the velocities. You see, I've labeled that 36 centimeters per second. Why in the world would I have done that? We don't get 36 centimeters per second. We divide this by this, we get 18 centimeters per second. Well, you have to understand that the 18 centimeters per second represents your average velocity, not your final velocity or not your initial velocity. It's the average velocity. Okay, what do I mean by, what's the significance of average velocity? Go back to what we said here. The average is what you would multiply by the interval here to get the area under the graph. Okay? Now the graph is, bounds a triangle. If 18 centimeters per second was the final velocity, then it wouldn't be the average velocity, okay? Because if 18 centimeters per second is the average velocity and we multiply that 18 centimeters per second by the 3 seconds, I'm not sure I said that right, so let me say that again. Okay, if 18 centimeters per second is our maximum velocity, we multiply that by 3 seconds, we get 54 centimeters, right? But that doesn't represent the area under this triangle. That represents the area under this big rectangle. So if this was 18 centimeters per second, if your final velocity was 18 centimeters per second, well, the area under the big rectangle would be 54 centimeters, and that would represent your average velocity times time. That would represent a displacement. That would represent a 54 centimeter displacement. Well, in that case, the area of this triangle here, the area under the straight line curve, or straight line graph, would be half of that, or 27 centimeters, which means that the displacement for this interval from 0 to 3 seconds would be only 27 centimeters, only 27 centimeters and not 54 centimeters. Okay? Now, I asked, where do you think the average velocity would occur? This is the final velocity. That can't be the average velocity because we started, that's the maximum velocity. Where's the average? So I said, well, in the middle. Well, I could ask in the middle of what? Middle of the x interval, the middle of the straight line on that interval, the middle of the y, or the v vertical axis interval. But yeah, I didn't make too much of that. I said, okay, let's go to the middle of this interval, which puts us at the middle of this straight line, doesn't it? Because the straight line has a constant slope. Okay, constant slope means that this triangle here, which has a run of 1.5 seconds, has to be geometrically similar to this triangle here, which also has a run of 1.5 seconds and the same slope. Now you really need to sort out why it says that. Why does it say that? It's because the rise of the triangle is equal to the slope multiplied by the run. That's because rise divided by run equals slope. And it's not atypical that, you're still sorting that out, although you should have sorted that out long ago when you took calculus. So, from the meaning of rise, run, slope, and the fact that the slopes are equal, these triangles have to be similar, geometrically similar. Which means that they have the same rise. Okay, well, if the average velocity occurs at this point of the graph, that's going to be 18 centimeters per second, which means the rise of this triangle represents 18 centimeters per second. So the rise of this triangle has to represent 18 centimeters per second. So that the total rise from here to here is going to be the rise of this triangle plus the rise of this triangle, or 36 centimeters per second, which means that this point represents a velocity of 36 centimeters per second when the clock time is 3 seconds. Okay? Now you really have to understand all those relationships. You need to think about every statement I made and why it says what it says and why it's true and what it says about the motion. And that takes some real sorting out. That's not at all easy. But once you have it, once you've reasoned it out, you can apply the same reasoning to situations that have nothing to do with motion. Other situations are going to involve work, energy, momentum, etc. The reasoning is always the same, just that the units are different and the meanings of what's graphed is different. Okay, well, in any case, for the straight line graph, the average does appear at the midpoint, and you can prove that using a little calculus, and you can prove it not even using calculus. We then conclude that the graph has these characteristics, the numbers that I've labeled: the average velocity at the midpoint, the final velocity at the end point, and constant slope, meaning constant similar triangles when we divide things at the midpoint. Using this, if we multiply the average value times the time interval, the average value is 18 centimeters per second. The time interval is 3 seconds. We multiply that out, we get 54 centimeters. 18 centimeters per second times 3 seconds is 54 centimeters, because of course you got the 18 centimeters per second by dividing 54 centimeters by 3 seconds. Okay? So now the area under this graph corresponds to the displacement, as it must. Okay? So that's a displacement during the interval, and that's now nice and consistent. Wouldn't be if you thought the 18 centimeters per second went up here. The slope, well, that's rise divided by run. That took us a while to reason this out. Okay? And understand what these quantities are. Okay? But you get either 18 centimeters per second over 1.5 seconds corresponding to this interval, And I'm going to have to shut up because I'm running out of time here. I'll pick it up in the next.